Okay, hi everyone. Thanks for joining me today. I'll be going over the S1 simple test time scaling research paper, but I actually won't walk through the paper. I'm just gonna give you some of my takeaways and how it can add value to myself and possibly to you. So first things first, let's do some introductions. My name's Ronell. I have experience in a lot of different industries, mobile games, parking, real estate, EV, and currently I'm a software dev manager at a billion-dollar e-commerce company. And my AI learning journey has been about 2 years. I started at Fast AI, did a bunch of Hugging Face stuff. I built some RAG, knowledge graphs, agentic frameworks. But ideally, probably my best accomplishment was I was able to get my son into university. So I think that was my main goal. Currently, I'm trying to bridge the gap between research and enterprise. And if you're in the industry, you know it's a huge gap. And also currently trying to build an AI center of excellence where I work. For this specific paper, I wanted to learn how to train domain-specific reasoning models for enterprise use cases. And what's interesting about this paper is that it's actually really simple. I can explain in about 5 minutes, but I realize that everyone here is of different backgrounds, so I'll just start from the beginning. Otherwise, it might actually be confusing if I just jump right into it. Okay, so first thing you need to know is LLMs are just next token predictors. If you've ever talked with ChatGPT and had a conversation, there's a lot of magic that happens in the background and a lot of stuff hidden behind the scenes. And all it's really doing is predicting the next word after your question or anything that you say. So at the end of the day, uh, ChatGPT's actual model is just a neural network, and it uses the context as its working memory. And so think of, for all the people in the tech industry, they know what RAM is. Just think of context memory as RAM for the model. And then that whole, once it predicts the next word, it just feeds it back right into the model and then predicts the next word. And then it keeps doing that until it gets the stop token to get the final response. If you're going to take away anything from this presentation, I think this is probably the one thing maybe to take away from, because it's fairly fundamental. It'll help you understand everything else that's going on in the industry. Okay, so if you're still confused, don't worry. I will have a AI generated diagram. So the LLM token prediction process really just happens like this. You ask a question, how do LLMs work? It breaks it up into tokens. Think of tokens as sort of just unique, like chunks of words. Most of the time, it's like 3/4 of a word. But I usually, just for simplicity, I always just say word, next word, because no one really understands what token means. And then so you feed it this question, how do LLMs work? And all it will do is it'll just predict the next words like after that based off of the training data. And I hope that makes sense for everyone. If not, you can stop me. You can stop me at any time or post questions in the chat and I'll go stop. Okay. This is another important concept, system one versus system two thinking. What I just showed you is actually system one thinking. And system one thinking is sort of like for people, it's the first thing that comes to your mind, just without really thinking, it's your gut response. System two thinking is like your response after you think about whether to respond that way or not. And so a good example is if you're at work, I'm going to ask you a question and maybe you first thing that comes to your mind is an inappropriate response. And, you think in your head, should I really say that or not? Right? Yeah, so system two thinking. So I kind of just made up this definition. Consider that the first thing that comes to your mind may not be the right thing, and consider other options and rationalize your best answer. And when that definition will make sense once I go through the next one. Okay, so then the latest innovation with models is the thinking, system two thinking. And so this was introduced with OpenAI's O1 model and also DeepSeek R1. when the models first came out, I was really blown away. I was actually kind of wondered how they were able to show or get models to think. And I actually thought that maybe there was an additional process on top or as an agentic framework. But what I actually realized was these thinking models are still next token predictors. And so it's not much different from the original model. The only thing different is that they added extra think tokens to mark the beginning of the thinking and then another think token to mark the end of the thinking. Okay, and so just hold on to that thought for a second because a lot of things will make sense that, that's really the only extra thing that thinking models have. OpenAI doesn't actually expose their thinking tokens. So when you actually use OpenAI, the O1 model, it just shows a bunch of stuff, but it doesn't actually show you its chain of thought. DeepSeek R1 does, and then you can actually see that you can actually see it thinking going through the process. Yeah. And is everyone still okay? Good. Okay, I'll move on. Here's another example. And this is just an addition to the other slide that I had. So how do LLMs work? It goes through the token prediction engine, which is the LLM, and then now it starts the thinking process. So here's your start thinking token, then it goes through its thinking, all that. Then right at the end of the thinking, hold on, I just realized I had a pointer here. Okay, then it will go down the final response, and then yeah, and then now it'll just do that. Yeah, so thinking models, they actually just produce a lot more tokens. But the thinking process is a lot more transparent. Okay, cool. Okay, so far, everyone following? So how are thinking models trained? LLM training mo data isn't actually all that glamorous. It's just question and answer pairs. If anyone can look this up, just go to Hugging Face and you can actually see it's just literally what is this or how is this, and then questions and then a lot of answers. LLM training data actually contains an extra thinking trace, which is a chain of thought before the answer. You got your question, you got your chain of thought, and then you got your answer, right? So what's interesting with R1 was it was the first model that actually showed the training methods, and it used a reinforcement learning technique to generate the chain of thought thinking traces. And so this is fairly new because they weren't actually created by humans, which is kind of interesting. Then those chain of thought thinking traces are then used for traditional. What's interesting is fine-tuning a non-thinking model to think is actually significantly lower cost than training something from scratch. So maybe we can make it a bit interactive. How much cheaper and how much data do you think you need, like, to train a non-thinking model to think? So if I guess like for anyone that's already read the paper, you already know, but if anyone wants to take a wild guess, you can put it in the chat.
Oh gosh, last time I checked Wikipedia, it's like 20 gigabytes. Depends on if you have metadata in different languages.
Okay, so this is gonna
I
blow
would
your
say, I don't know, 1 terabyte.
okay.
No idea.
Okay, so this is gonna blow your mind. So last month, this is the research paper I'm referencing, right? It's called S1 Simple Test Time Scaling. They actually were able to train a thinking model with only 1,000 rows of data. So so think about that, like how much savings that is. They curated this data. So first what they did was they got really hard questions, PhD level exam questions, math contest questions, like the hardest of like normal human beings can't answer these questions, PhD level questions, right? And they got 59,000 high quality reasoning traces. Originally, they used a Google model, and then afterwards, they used a R1 to create these traces. And so they use a heuristic and they basically ran it against existing frontier models. And they said, is can this problem be solved easily with this model? And if it could, then it rejected it because it was too easy. And if the reasoning trace was too short, then they just rejected it as well. And when they used those two criteria, then they actually got it down to like 1,000 rows. And what they did was they got an existing Quen 32 billion parameter instruct model as base. And so that's a non-thinking model. And if you actually think about how big this model is, it's actually, if you actually get like a quantized version of it, you can run it on your computer, like a desktop computer. And so when they trained this model, they fine-tuned it on 16 H100 GPUs. They trained it for 26 minutes and it actually cost them only $6. That's pretty amazing, right? So 1,000 rows of data and $6 of compute. And they didn't actually stop there. They actually did something else pretty innovative. They did this thing called budget forcing. Inference time scaling is kind of interesting because what you're doing is you're manipulating the context to make the model have more accurate results. And so the model itself has static weights, so you can't really change what it knows, but you can actually change how it thinks, right? And the Stanford guys, they were actually thinking about this problem. They said, hey, what can we do to make it think longer? And remember, the thinking process is just governed by a start think token and an end think token. And so what would be the simplest way to make it think longer? They came up with was super simple. And all they did was exactly that. Yeah, they just ask it to think longer. And so they basically created a minimum budget of tokens to think. And if the thinking process didn't meet the budget, all they did was they replaced the last think token with the word wait. And so what this did was when it went back to the cycle of the next prediction into the LLM, it forced extended thinking. So it said, hey, wait, and then it basically just did more thinking, right? And then there's another process here that says that just keeps checking, right, to see if it meets the budget. And then it finally hits the final response. So who said Alexandra? Yeah, ask it to think longer. 100% correct. Yeah. So this was maybe a fairly simple method. Any questions around that? Is that pretty straightforward? Okay, so budget forcing summarized. What does think longer mean? Okay, good question. Okay, so I'll go back to this, right? Remember I explained that this is what happens in a regular thinking model. It goes through, it says, hey, this is what maybe how I should answer the question. And then it says, okay, I'm done thinking. Now I'm going to give the final response. All it does is it replaces this last thinking token right here with a word. And so I'll go back to this thing here. And so it basically just says we sort of say define a budget. And in this example here, we put a budget of 50 tokens. And when it goes through the thinking process, it says there's only this thinking only used up 32 tokens. So I'm going to go and replace this thinking and tell the model to think longer. So it's sort of like a nudge. And then it gets replaced with the word wait, and then it gets fed back into the LM, and then it starts the prediction again. Okay, I mean, where does the additional context for more thinking come from? Where does okay. I'm not quite sure I understand your question. Hold on.
I
Okay.
think I understand the question. So I believe the challenge is that the model is autoregressive. So its output becoming its input in the next state. And that trick that Rano is now explaining is that when it generates token to stop thinking, we are swiping it and replacing, and it thinks that it keeps continuing, yeah, with this wait token. So that's the deal.
So the input of that is that if you don't put the weight or if you just let it run normally without extended thinking, then it'll go to a certain budget threshold by itself and then stop thinking and move on.
Yeah,
Or
it'll just go straight to the final response. It'll work as if you didn't budget the or you didn't it'll just ignore the budget basically if you don't replace the weight. It'll just work normally.
Okay,
Yeah.
thanks.
Okay. That was a good question. Thanks, Mike. Um, okay, so budget forcing summarize. Okay, so this is the just the heuristic. I just want to go over it again. So if you wanted to implement this yourself, what you do is you set a variable to set the minimum budget. And then during the thinking process, you count all the tokens. And if the total thinking tokens is less than a budget, then you replace the end of thinking token with the word wait. And then you send the context back for up to the LLM. On the other hand, if your tokens or your thinking tokens has exceeded the budget, then you actually force the end of thinking by inserting the end of thinking token, right? And then you send it back for the final response. If you've ever run R1 locally on your machine, sometimes it the R1 model actually just thinks forever and then it gets into this infinite loop. And so this actual exceeding the budget token check here actually fixes that. So that's pretty cool. Some other things to consider as well is just make sure your budget is less than your context length. So this is sort of more important when you're running it locally on your desktop, but less important when you're running it on a server. What's also interesting is the word wait can actually be replaced with other words as well as other words so specific to your domain. So depending on what you're training, you can say, but what about, or have I considered all the options, and then this will sort of trigger more thinking as well. Any questions around this? No? Okay. Okay, so you can actually try this out on your own. You could just go to the GitHub. The I think right now they have set it up for a max total thinking budget of 30K tokens. You can also even just replace the encouragement token, which is wait right now. And then I just said, you can replace this with other things. One of the other important things is just to make sure that you have clear delimiters for thinking and answer and the training data on that. Okay, and so how did it do? These are frontier models up here, right? And so all of these models are at least 150 billion parameters. This down here is what was actually trained. And what's interesting is the results for here. One. You'll notice that for the math results, the math 500, it actually beat O1 Preview and O1 Mini, right? And got really close to O1. And O1 is considered, the one of the best thinking models right now. And this one here, you can actually run on your computer. So think about like how powerful this method is, right? And it only, 1K of data, if training data, $6 of compute to train, and you have something that actually works as good as some of the frontier models, right? Any questions about this result? Is it
I
quite
have I have one question. Maybe I didn't get it at the beginning.
sure?
Uh, you mentioned from one hand that they use reinforcement learning to uh, kind of generate that chain of thought, but also that they used some available sources to curate that 1,000 of data points for fine tuning. So I'm thinking, is it like mixed technique or I didn't get that right?
Oh yeah, so for the reinforcement learning example I actually just gave for R1. I was just saying that it was a method of getting a chain of thought. But for this specific model, they just used it's just standard supervised fine tuning.
Okay. And they
Yeah.
were just forcing the model to think longer.
exactly, yeah.
get the
And
right answer.
exactly, yeah. The key thing is that you need really high quality reasoning traces, right? They also did an ablation study um, where uh, they checked to see if it's really like 1,000 rows is all you need. So then they did they got all 59,000 and they retrained the model and they checked the benchmarks and it wasn't actually that much better than the 1,000 rows. And they removed data, they added data, they just tried to see if the 1,000 rows is all you need. And they're able to figure out that yes, if you have 1,000 rows of high quality data, then yeah,
I see.
then
One more question.
sure.
If we have 1,000 examples with those chain of thoughts, isn't it more like a supervised training problem?
It is, yeah, 100%.
So
Um,
why the model doesn't try to just imitate and replicate those given examples? And instead we are kind of like still forced to think longer.
yeah, so what I my main takeaway from this is that chain of thought has been around for a while, but what they did because they delineated like when thinking starts and thinking ends, now you have a mechanism to make it think longer and check its answers, right? Without those delineations, then you just have basically a regular chain of thought model, right? I don't know. Does that make sense?
Okay, I think I get it. I have to think
Yeah.
about it. Thanks.
Yeah, yeah, yeah. Um, okay, I'm getting close to the end, but I just wanted to just maybe take three there are three big takeaways from this presentation. One, you only need 1,000 rows of high quality data. And before this, I actually thought maybe you needed 100,000, you needed 1 million. And it was really out of reach. You need to hire a data scientist to like, sort this out and all of that. But 1,000 rows, if you are a super expert in your domain, you can make this manually. Like so it's within reach. And I always thought, if to train a model, you need millions of dollars, and it turns out you only need $6 for that. So now it democratizes training, right? And the last takeaway here is accuracy can be improved at inference time. So if you have programming capability, then yeah, you can um, mess around with how the think tokens are generated, and you can use it to improve your accuracy as well. Okay. And back to originally my first slide, I had like a lot of interest in this because, I'm in the enterprise space and trying to bridge the gap between AI research and enterprise and how could I leverage this for enterprise. These are sort of the first things that came to mind, and I'm sure you guys will probably have some other ideas as well. In a world where, we have to keep all of our systems up all the time. And I think one of the useful cases here is to train a model to analyze production logs. And there's always issues that happen all the time. You get called 2 in the morning, and is it a real issue or not? You look at the logs and you're like, okay, no, this is not an issue. Why did it call me? So if you train a thinking model to be able to analyze production logs and make a decision whether to escalate, that would be useful as well. The other one is an employee onboarding agent. I think everyone's been a new employee at some point in their lives, and you probably have pinged about a dozen people asking questions about where things are, how to find things, how to set up your environment. Having an employee onboarding agent will just make things a lot smoother. I think a help desk AI agent is fairly well understood. But this one's kind of interesting. I noticed that in large enterprises, a lot of applications and services outlast careers. And what I mean by that is a lot of people they stay in a team or a group for maybe 2 or 3 years and then they move on to other better things. And then then they take with them like domain expertise. And so what if you can have a reasoning model that is like the SME of like that service, and it would be the one to do the code reviews. It'd be the one to sort of let understand the impact of changes, things like that. And so that's something I've just been thinking about as well, because at the enterprise where I work at, we have systems that are over 10 years old that we're still maintaining, and there's not a whole lot of people that know or have expertise in those areas. So some final thoughts as well. So I've been in the industry a while, so I had this like idea, reasoning traces can be programmatically generated. Like really, if you think about it, it can be application logic, it could be standard operating procedures, it could be generated from existing data, right? And the other thing too is how many times have you asked a model a question and got it completely wrong and didn't know why? And so now reasoning traces offers a way to debug a model's thought process. And so if you go through that cycle where you train a model to think a certain way, and then now you're able to validate it, and now you can correct the data, this is actually like the new programming paradigm, right? So my thought here is, hey, could this be the new programming paradigm for the future and the way that we build software, right? So that's kind of my thought there. And there's some references. Uh, so any questions? We're at the end of the slide. And if anyone wants me to go back to any slides, I can. And hold on, there's a question here, Thomas. Okay. Okay, so in the context of reasoning model, this seems to be just more advanced chain of thought reasoning. Yes, that's exactly what it is. Essentially chain of thought, but also rethink the COT, do it X times up to configuration limit. Yep, that's correct. So because of the apparent need of 1,000 reasoning traces, then what you're suggesting is that with domain knowledge, a person can craft a training data set to reason, analyze with the same steps and varieties, same use case of an expert, yes. So that is the benefit of being able to cheaply train a small open source model to have a, yes, exactly. Exactly my thoughts. We don't need a frontier model. If you want to train a model for a very, very specific use case, you can probably train a 7 billion parameter model and, you know, actually even a 3 billion parameter model, like with the R1. But yeah, it's pretty amazing now what we can do. And yeah, that's exactly use case. So awesome. I'm glad that this was a takeaway for you, Thomas. That's exactly what I wanted you to come away with. Okay. Any other questions?
What do you see the impact of this on, if you will, the tens of billions of dollars that have gone into the major LLMs?
I don't think it's going to change anything. So the what those guys, when I say those guys, I'd say like the companies building frontier models. What they're after is AGI and ASI, and they're just racing to uh, to get that. And they're gonna need as much hardware as they can. And I'm gonna go back to the very, very first slide, right? And the reason is this. LLMs at the end of the day, they're just next token predictors, right? And a lot of the reasons why they need the hardware is because the more hardware you give, the more parameters you give, a lot of more emergent behavior happens. And the next token predictor starts actually creating, doing some pretty amazing things. Like it starts following instructions, it starts doing, um, it starts doing some useful stuff. And the current thought is if you give it more hardware, give it more parameters, it'll just get smarter. And eventually we'll get to a point where, hey, maybe we'll achieve AGI. So I'm from the enterprise world and I'm thinking, hey, I just want to not get called 2 in the morning. And so I just want to build a reasoning model that just knows if this is an issue or not. And I don't need a frontier model for that. I just need to train, maybe a 3 billion parameter model with the last year of error logs and, what we did. And then that's it, right? And you don't need, yeah. And I don't care if it, knows all of the, or can pass the bar exam or medical exam or pass a math 500, test, right? So, I just wanted to do a very simple thing. And what this does is it actually enables that, right? So sorry, I kind of went off. Mike, did I answer your question?
Yeah, and you're probably too far advanced for my understanding of the technology. But the impetus of what you've said is that 1,000 lines of better data, for lack of a better term,
Yeah,
um, significantly improves results or use on certain use cases or specific use cases.
yeah, that's exactly.
How, and I guess my question is, wouldn't that imply that rather than, as I said, bigger open source or bigger LLMs, wouldn't that imply that LLMs would get more specialized going forward? So why wouldn't everyone take, especially given the cost benefits, rather than pay, um, $20,000 for access, if you will, or for compute time? Why wouldn't you take, a smaller, even lesser model, run it locally, but put your own, if you're an enterprise, put your own 1,000 lines of data in it, and then be getting better responses that way?
Yeah, that's exactly why I did this presentation. Yeah, you basically got the point. Why wouldn't you do it? This is makes no sense to pay for huge enterprise license for a model that does more than I need, right?
Yeah.
And so if I can just train a model very cheaply and then why go the other way? Right.
But AGI aside, that has huge implications on whoever doesn't get to AGI, because at a certain point, the LLMs will be good enough, and then, each company or each particular task can hive off their version of it to run their particular their product, and not need to pay, as I said, the exorbitant fees for uh, recouping the ROI for some of these investments.
Yeah. So the other thing too to understand is uh the frontier models, they're trying to go for general intelligence. And so they want to make it useful for everyone. So think of it as a consumer product, right? When you go towards like enterprise or business, um, there's a lot of custom knowledge or domain knowledge that's not publicly available and will never be, right? And so all of these like ChatGPT and all of these frontier models, they won't know business processes, they won't know specific domain knowledge, and they never will, right? Because companies will never give up those secrets. And so what this will offer now is an alternative to just train something internally, and sort of build something. Um, I don't know. Does that make sense?
Mhm.
Yeah. Uh,
I have one more comment or question
sure.
because now I'm thinking they use only 1,000 examples. And my question is it more to acquire new knowledge or more to force already available basic model to think better? So the actual knowledge about that domain and universe was taken from that human, right? And the examples are primarily to kind of force this particular way of extracting the knowledge. Or maybe it was the knowledge itself, but then you would think intuitively that, well, the knowledge must be limited to only those 1,000 examples, right? There's nothing more.
Yeah. So I want to make sure I understand your question, right? I think you're saying, uh, does the model only know the
I can. Sure, I
what
can
it's
try
trained on?
rephrase my question.
Yeah.
If we take a generic English language prediction model, and now let's imagine I have 1,000 examples from my very hermetic domain that is not available anywhere. Uh, I would expect that any new knowledge that I'm introducing to the final model is limited to only that training data set. And in this case, because there is like a programming and general math exercises, I think a lot of knowledge was already in that queue and to start with. But that process of fine tuning, forcing it to think better, kind of like added new layer of operationalizing, better extracting this knowledge. It's kind of like my comment, my understanding, but also maybe question. Maybe you have your opinion about that.
Yeah, yeah. You know what? I get what you're saying. So I think so because now we can have this facility to make it think better, like sort of control the end of thinking token. Maybe we there's a way to pull out some of that extra knowledge that it was sort of already new. And yeah, and I think you're right. There's the models right now, they're basically trained on the world's data, like the entire world, right? Like everything that's ever been written, which is pretty crazy. But the main problem with the models right now is if you don't ask it the right way, how it doesn't even get the right answer. And so there's a certain way to even prompt a model to get correct answers. And so now that you can sort of control this method, you could you can actually experiment with this and actually get more accurate answers, right? So um I think that's what you're trying to get. I know hopefully I got your answered your question.
Yeah, sure. Thank you so much.
Yeah. Okay. I'm just reading the chat right now. So I think Thomas said that a common approach is to prompt engineer a few reasoning steps, yeah, for a particular use case. Yep, that's a common approach, and that's another way to manipulate the context to get more accurate answers. So I've been playing around with LLMs for about 18 months. And so one of the things I figured out with instruction tune models is that you can sort of treat it like a like English as a programming language, and which is kind of interesting. So I did a huge experiment on this to see if actually that was true. And I built a GPT to solve Wordle. And I don't know if you ever use ChatGPT to solve Wordle, it's the worst. Doesn't give you correct answers. But just through prompt engineering, I was able to actually create like a pretty solid one. So, any other questions? We're approaching 1 minute left.
Oh, just wondering what you think about what I said before that about the RAG system with the reasoning traces instead of fine tuning a small model, but using a RAG with reasoning traces on and a large model.
Hopefully, I can unpack what you're saying. Can you just maybe give me an example?
Uh, sure. So, like a user will ask, prompt a question, and then with that question, you'll have some sort of logic that determines what kind of reasoning steps is the best for that to answer that question from a RAG database. And that
Yeah,
RAG database could include those reasoning traces that are used to train models, right? Different types of ways to reason, right? And
yeah,
then
yeah.
that's for a large model.
Yeah, what you're actually describing actually is the router in a agentic framework. Yeah, so yeah, 100%. You can train model for specific use cases, and then depending on the question, then hey, I'm gonna get this guy because he's got really good tools or trained a certain way so that it produces the proper reasoning traces, right? So yeah, you can definitely do that. Okay. All right. If no more questions, then I'm going to wrap up. All right. Say thanks everyone for joining me today, and I hope you guys learned something new.
Definitely. Thank you, Ronald. It was very
Thanks, Ronald.
interesting.
Okay. All right. Thanks everyone. See you.